Hello everybody, we're going to talk about significant figures. At the end of this presentation, you'll know how to count significant figures in a value, but you might not know how it's going to be used. So pay attention to the second video where I talk about rounding and all the rules for rounding. Okay, it's very critical to be able to write down the correct answer with the units and the correct number of digits that comes out from our calculators. Okay, now there are two types of numbers. The first is exact numbers, and the second are measured numbers, okay? So exact numbers are counted or they're defined, and by definition they have no error. So for example, we have 1 foot is equal to 12 inches. That is by definition 12, so that's exact. All other conversion factors, we are going to assume that they're exact. Our other measurements are usually going to give more error, okay? This calculator, for example, has 38 buttons on it. 38 can be counted, and that's an exact number. Now it's true, maybe a kindergartner or somebody might lose count and make a human error, but we're not talking about human error, okay? We're talking about things that only come in whole numbers. The number of pencils in a box, the number of students in a classroom, and even the number of atoms that might show up in a chemical formula. H2O has exactly 2 hydrogen atoms in the formula. As science advances, we won't figure out that that's really H2.1, okay? Measured numbers are things that you, of course, measure. So here in this figure, we have a voltage, which is being measured by a voltmeter. Even though it's digital, there is error associated with that, okay? We have the mass of a steel wool there. I accidentally zeroed the balance, I guess, but it has a mass of over 5 grams. We have a couple of thermometers there, and we have a ruler measuring the length of a rod. All of these examples are measured numbers, okay? And they have error, usually in the last digit of the value you get, okay? And these numbers are going to come from lab experiments, maybe word problems, or measurements, as you know from the units, okay? If somebody said 3.8, okay, 3.8, that's a number. But if somebody said 3.8 gallons, then you know, okay, gallons are something that's measured, it's not defined, and so 3.8 has some uncertainty with it. All right, let's talk about mass. This penny here on the balance is reading 2.50 grams, okay? That is not an exact mass. The balance has an error, as indicated here with the plus or minus 0.01 grams, okay? The error of this balance is plus or minus 0.01 grams. It has an error in this last decimal place, okay? This means that the penny could weigh as little as 2.49 grams or as much as 2.51 grams or any weight in between, okay? This balance has inherent error, both from the calibration and the operation of the balance, okay? Volume also has an error associated with it. This graduated cylinder here contains 24.5 milliliters of water, okay? Now, you're going to have different kinds of glassware, some plastic, some glass, more precise, less precise, and you're going to have Class A, Class B, Class C, you know, kind of glassware, okay? So this one here has a rated uncertainty of plus or minus 0.5 milliliters, okay? And the error of this graduated cylinder is plus or minus 0.5, okay? So when you're reading this value, you might look at the level of the liquid of water, and it might read exactly where it's reading, okay? And 10 other people might all agree it's right there at 24.5, but the glassware might not be uniform. It might be wider or smaller. The printing of these lines on the outside of the glassware might be shifted off a little bit. And there's many types of things that go into the manufacture of this piece of glassware. So the inherent error associated with this graduated cylinder is plus or minus 0.5 milliliters. So if it's poured out, this one's calibrated to deliver, or TD, it might be 24.0 milliliters, or it might be 25.0 milliliters, okay? Or any volume in between. And again, this glassware just has inherent error. Now, what about significant figures? What's this all about, okay? Now, every number that is part of a measurement is going to have a significance or be a significant value in that measurement, okay? And there's 3 types of numbers here on this slide, okay? The pesos per liter down here on the bottom is defined by the gas station, okay? 22.99 liters is measured, okay? You're topping off your tank of gas tank, and it's reading 22.99 liters. So that's measured, and that's what has uncertainty. The pesos up here is being calculated by the computer that's in this gas pump, okay? So we're going to focus in on just right now, not calculations right now, but we're going to focus in on errors in measurements. Okay, where do we find exact numbers? Exact numbers are going to show up all the time in equivalencies or conversion factors, okay? Exact numbers have unlimited precision and therefore infinite numbers of significant figures. So for example, if you look at this definition right here, 1 foot is equal to 12 inches, okay? The 12 is really 12.00000 forever inches, okay? It's infinitely precise. It's not, we're not going to determine later that it's 12.1 or 12.0001 is defined to be 12, okay? Here's another one from the OpenStax textbook. 1 kilogram is equal to 2.2046. 1 kilogram is exactly 1. It's an exact number from the definition, okay? Now let's look at some significant figures and the examples. So again, any number that's in the measurement is going to be significant and part of that measurement. You're always going to have units associated with a number, so don't get confused or be worried about, okay, what's the G or the ML or the L or the G stand for, okay? So let's look at these. 2.49. We have the 2, the 4, and the 9 are all part of that measurement. So this has 3 significant figures. This next one, we have 3, we have a 9, we have the 0 in the middle, we have the 4, and then the 2. So all of those are going to add up to 5 significant figures, okay? We have 3.00. So this guy here has 3 significant figures. This one here, 4020, those are all part of the measurement, so there's 4 significant figures there, okay? Now, it might get confusing when you have zeros that are leading or before the first number. This is what you need to remember. Left zeros do not count, all right? Let me explain why. Now, in this value right here, we only count the 2 and the 5, okay? This has 2 significant figures because these zeros on the left are just a decimal placeholder, okay? 0.0025 grams is the same thing as 2.5 milligrams, okay? Now, if we were to look at this value, 2.5 milligrams, we would say, yes, it has 2 significant figures. I get that, I understand that. But this representation must also have 2 significant figures. It can't be more precise just because we want to call it a different unit. So this also has 2 significant figures. The only way we can arrive at that conclusion is to not count the first initial zeros, okay? So just remember that zeros at the beginning of a number, before the first digit, do not count. One of my students learned in high school and shared this with me. His high school teacher said, think of your number as the United States, okay? You have a whole bunch of zeros on the left, you have a whole bunch of numbers in the middle, and even at the end, and S stands for seconds, by the way. And he said Pacific Ocean zeros don't count, okay? So here's the ocean. We're just going to cross all these out. How many total significant figures would be in this value? Well, we count the numbers that are left. So you just count them up. Okay, the 4, the 0, the 2, the 3, the 4, the 5, the 0, the 0, the 0. Okay? So let's practice. How many significant figures are there in 3.90 liters? Okay? Pause the video and think about this. How many significant figures are in 2.00 seconds? Okay? How many significant figures are there in 3.9 times 10 to the minus 4th kilograms? And how many significant figures are in 0.0063 grams? Okay? Now, we haven't talked about something like this in part C here, but all of this business here, the 1, the 0, the negative, and the 4, are all designed to hold a decimal place. So we don't count any of that. This is just going to have 2 significant figures from the 3 and the 9. We could write this as 0.00039, which, you guessed it, also has just two significant figures. So the 10 to the minus 4 part is the factor of the scientific notation, and it's not counted as being significant. Okay, so I hope this video helped you. Thanks for watching.